synthesize them. You just have to do chemistry on your glass bead, and then you can attach this group pretty readily. This is succinylate, essentially. So if you count 1, 2, 3, 4, 5, this is basically, you can imagine how it goes from something like that. Right? Again, from the NH, and then you can attach your succinylate to, in this case, the ester, and so on. So this is the succinyl, this is the succinoyl group. It's probably again 1, 2, 3, 4, 5. This is basically the ring attached to a bead, and then attached to your nucleobase. The next step, basically, you do with DCA, which is like chloroacetic acid. And in this case, first step is the protected. And then at this point, you're typically working from anywhere from, I guess it depends, from 1 micromole up to 1. Now they do up to the minimal scale, even in solid phase synthesis, but that's industrial scale. Typically, in the labs, most labs is going to get the micromole scale. The first step is you synthesize, and this has to be, you do the DCA, dichloroacetic acid. Right, so less acidic than PFA, trichloroacetic acid. So you think with DCA, you want to be careful that you don't knock off the silane group, and then in this particular case, you add your coupling reagent. And this is a lot of times you add your phosphoramidite. This we talked about this last time. Here's the cyano. In this case, I'm going to call this B2, I guess. And then a 3. So in this particular case, the next step is you're going to couple these 5' hydroxy. In all the synthesis, you start from the 3' end. So your solid supports are attached to the 3' end. You start building it up. And in this particular case, nowadays, this is something like that. The ethyl tetrazole. So tetrazole has 4 nitrogens. Right? So imidazole has 2 nitrogens, triazole, and then tetrazole. So tetrazole is a typical coupling agent. It's an activator, so it's basically going to activate your phosphoramidite so that the alcohol can attack it in this particular case. You certainly have better pictures in any book that you find. So that's your next step. So basically, you do your coupling in this particular case. Right, so you go from the phosphoramidite, you're coupling the 5' hydroxyl group. In the presence of tetrazole, this is your activator. Your tetrazole is going to react with the phosphoramidite, isopropylamine leaves, and then your 5' hydroxyl group attacks, and that's how you end up with your linkage in this particular case. Then the next step is you do oxidation. The presence of iodine, pyridine, and water. In this particular case, and there are other types of oxidants, so this is certainly not the only one. And that's your product in this particular case. The oxidation essentially is to, remember this phosphorus is going to be very reactive. It wants to immediately be oxidized. or react with something else. So one of the main reactions, it gets oxidized, in this case, water. Well, I start with iodine, this is going to attack iodine, and then water is going to displace the iodine. Pyridine makes it, it's under basic conditions, so you can go to the phosphate. In this case, a phosphotriester. And that's the story in this particular case. Then in this case, this enters the cycle. The cycle again. Right? So in this particular case, then you treat this with DCA, the chloroacetic acid, deprotect the 5' position, and then you add another phosphoramide with your activator, and then you keep building. So from the 3' end, you're building up to this is your 5' end, this is your 3'. So this is basically the essence of solid phase synthesis. There are other types of activators, obviously depending on the synthesis of what you want to use, you would alter the modifications. You can have different groups here. Depending on your modifications, some modifications are not cannot withstand the deprotection conditions from TBDMS. Oxidant, there are other types of oxidants as well. So some milder oxidants, such as terbutyl peroxide and terbutyl alcohol and hydrogen peroxide, and that would be the idea. Are there any questions with this? What I mean by solid phase synthesis?
I kind of didn't hear what you said about the oxidation step. What happens when it makes a phosphate? How does it make the phosphate?
Well, in this particular case, it's going to react with iodine, and then you have the iodide, and then water will come and attack. And then the first step, one of the H's will go with the I, and then the pyridine gets rid of the other hydrogen so that it can go. Then the driving force in this particular case is the fact that the phosphorus, in this case the phosphide, can go to the corresponding phosphotriester. Does that make sense? Then at the end of the day, what you do is you treat this with, let's say in this case that you wanted to just stop at your dinucleotide. So if you want to stop at your dinucleotide, you treat this with ammonia. So the ammonia is basically going to cleave off, because the ammonia, you can imagine, kind of like here, and it cleaves off the resin. So in your solid support, right, you get rid of it. Your CPG, you do at the end. And in this particular case, you free up your nucleoside. It's going to be, can be related, you can get rid of this. The NH3 in this particular case also gets rid of the ethyl cyano, so you can get actually your phosphate via beta elimination. Right? So you can imagine that how if you have a base here, it can go here, here, here. So you also get rid of acrylonitrile. And that's how you get rid of this. Now you have your phosphate linked with your nucleosides. Then at the end of the day, what you want to do, you just have to get rid of the TBDMS groups, and then you are safe. Does that make sense? Typically, we use on the nucleobases, you don't have to, but you can use protecting groups that follow up with base. So in this particular step, you do three things. Get rid of the ethyl cyano, cleave it from the resin, and deprotect your nucleobase. So you have the adenosine, for instance. We discussed this last time, right? It has to be protected. This case is a soil, for instance. It has exocyclic amine has to be protected, so that if you had an NH2, the NH2 could react in any of these steps. Right? So you don't want that. That's why it has to be protected. So in this step, you deprotect your nucleobases. You can also get rid of the benzoyl, cleave off the resin, and liberate your phosphate. Then one more step, get rid of the TBDMS groups with fluoride, and then you have your nucleoside. Okay? So hopefully next week, next week we're going to some specifics, and then I'll give you a few references on the new therapeutics that are being used, particularly on Patro, which is the one that was cleared by the FDA recently. You probably heard about that one, right? So it made a lot of news. So that's like the newest RNA drug that has been approved by the FDA. And so I'll give you some of those references so we can start looking into this. But first, I want to go over some strategies and think about how to functionalize and protect these nucleobases. Are there any questions with solid base synthesis?
Just to clarify, when you add ammonia, you protect all the bases that are present in that phosphate backbone, right?
Mm-hmm. Yeah, every nucleobase. So in the case of uridine is not going to be protected because it doesn't have any nucleophilic sites. So in the case of guanosine, for instance, a common one is it's acetylated. So you will see like this. And so the ammonia will protect your acetyl group. In the case of cyclidine, this is also acetylated. Right, so anything that has an exocyclic amine, the guanosine, cyclidine, or adenosine, in that step they only get protected. And that's what you want all of them to have, to be base labeled. Any questions? No? Makes sense? Alright, so how do we synthesize? In this particular case, the two main things is the series of your phosphoramidite, and then in some cases, the synthesis of your resin if you have a modification. If they're canonical nucleobases, then you can buy them. It's cheaper to just buy them. But if you have to modify them, then that's when it gets tricky. But that's when you not tricky, that's when you have to actually synthesize and prepare your own things. Again, in the book, in the link that I have online, and then I can share a PDF book that I have that describes this process pretty much neater and was in a little bit more detailed, not that much more. Alright, so a couple of things. We use a lot of silanes. Now, something I should say. This is, of course, for the RNA version, that you have the OH there. If the DNA, it's a lot easier. You don't have to deal with this group. So the DNA, you just treat it with ammonia. Basically, you have your DNA ready to go. But you still have to purify it sometimes. Sometimes it's just ready to go. Right, so the RNA, you have to deal with this OTBDMS group. And then one main thing that I commented last time is on the stability, things that you have to be very considerate about. You have your RNA. Let's just say it's an oligo. Right, so the main thing, as you guys probably already know, here is that the stability on the RNA degrades very quickly, certainly chemically on their basic conditions. So you treat these with any base, what's going to happen? Basically, you get cleavage. Cleavage, basically, of course, here. We have no minus. This can undergo essentially, so to open up, go to an intermediate, come back. Destroy it. So you can go with something like this comes back and opens up. Right, and then you clip your RNA. In the case of DNA, that's missing. Remember, there is no there's no 2' deoxy, so then they're very, very stable. So once you synthesize a DNA, you can literally spin on it. That thing is going to be very, very stable. Of course, you want that, right? Because that's your gene pool essentially. But in this particular case, the RNA is very unstable. Right? You treat its liminal base is just not degraded. That's chemically. And then in reality, when you treat with this, you also have to worry about ribonucleases, which can destroy your RNA. Ribonucleases, which are enzymes that target RNA to degrade it. So these are some aspects that you have to consider working in the lab. While your RNA is protected, you have no issue. Like if it has a PBDMS protection, you can treat it with base because you don't have an OH there. So this is not going to break. Once you treat with fluoride, you have an OH, and at that point, you have to worry about that. At this point, this is chemically protected with all of this, so there is no way a ribonuclease is going to do anything, right? But of course, what we're interested in is the RNA. And so these are the two things that you have to consider: base validity, and then the ribonucleases. For this class, we're not going to talk too much about the ribonucleases, other than the fact how some of the antisense technologies that are used right now trigger a function for RNA degradation. So we'll talk very briefly on that. And that has to do with the therapeutic applications. Are there any questions with this? And I think you guys kind of know this, I know it already, but just wanted to make sure. That's one thing there. Okay. So we talked about, so then what you have to do is, I guess, it's about protecting groups. Some of the common protecting groups that we use, which you have seen is the silane, PBDMS, which by now you guys all know it, that's therapeutic dimethyl silane. And in these particular cases, so that's one group. Another group that you commonly see is the interbutyl silane group. And so the whole idea here, the whole process, or the reason it becomes way more challenging with RNA than DNA from a chemistry perspective anyways, is because you have to worry about protecting selectively any of these atoms, right? So how do you do chemistry on this selectively over this one? They're both secondary, right? So there is really not much that differentiates. In this case, you could claim there is a lot of, it's easy to access because primary versus secondaries, so then easy to do chemistry. So in fact, reaction that's very common is if you treat the DNT chloride, pyridine goes exclusively to the 5' position. That's your trigger group. Remember we talked about the structure, how to protect, and the mechanism to get rid of the trigger group last time. Well, what if you want to do chemistry selectively on one of these atoms? right? So that becomes a problem. What if you want to introduce a fluorine in this position, right? So a lot of drug targets or drug RNA containing drugs have fluorine at this position. And so how do you incorporate a fluorine? That's part of an exercise today. But in the meantime, also a lot of them have a methyl group, a methoxy group here, so that your RNA doesn't get degraded. So if you put a methyl group here, you get rid of the H, right? But how do you put a methyl group without affecting those two? So that's one aspect. So one alternative to do chemistry here that has been done, there are also other ways to do chemistry, is that if you do we're going to do this one, chloride or three-flake, OTF. Essentially, any of these two groups, typically in the presence of silver nitrate, and in the three-flake, no silver nitrate. Some base, certainly, theory. Then what you do is so essentially the primary alcohol reacts first, and then there goes an intramolecular cyclization where this is in closer it's closer to the reactive side, and then this doesn't react. That's how you block the 3', 5' position, then you can do chemistry. So if you wanted to put a TBDMS group, you can do TBDMS, chloride, pyridine, and then how do you get rid of this? Basically, you treat it with fluoride. The problem is the fluoride can react here, it can also react here. But if you do it carefully and you do this reaction carefully, HF, tretinoamine, PHF, tretinoamine, at 0 degrees Celsius, if you do this reaction at 0 degrees Celsius in PHF, you can selectively deprotect this one. And then you end up, and this is just one strategy. As we keep looking at papers, you'll see other strategies and other things that people can do, or groups that you can use to protect this. But at this point, you can do chemistry here, or at this point, you can do chemistry here, and then eventually knock it off. So the main thing here that I want to portray before we go into some papers is the fact that you do have to be battling, or not battling, strategizing to protect selectively the alcohols. The other thing that you have to be aware of is that your nucleobase is nucleophilic, so that's going to pose problems as well. So you want to protect it, or in some cases not protect or change your strategy depending. Okay, are there any questions? No? You guys are ready? I think we talked about nucleophilic aromatic substitution next time. Please. Alright, so you guys have a chance to check the papers out. Came by a paper? Maybe. Okay. So the first thing is the form. So the first two pages, or the first page and a half, are basically from the same paper, the Chem Biochem paper. The references underneath is the reference I gave you guys last time. And then the second page, second half, is a different paper. It's a JOC paper, and you can see the reference there. Right? So just keep that in mind. Of course, if you open the paper, it's really clear what's where. So let's look at the. Let me see. Here we go. Okay. So on the first page, you have nucleoside number 4. You see it? Everybody on the same page? Alright, so take a page and write your name on it. This is for extra credit on the upcoming quiz. Yeah, does anybody not have a piece of paper? You want one?
Yeah. Thank you. Appreciate it.
Alright, so everybody has a piece of paper. Yes. So you see nucleoside number 4. Right? It's a timing. So let's say that if you start with methyluride, everybody knows what I'm talking about. When I say 5-methyluride, look at your notes and then propose a synthetic strategy starting with 5-methyluride. There's 5-methyluride. So you can purchase 5-methyluride. You guys also. So let's spend 5 minutes to propose a synthetic strategy starting with 5-methyluride to go to number 4. Again, this is for extra credit, and the next quiz is going to be next week. And if you guys have 100% on the quiz, then this doesn't count. Right? So this is just, yeah.
So I'm confused. So I'm starting with 5-methyluridine and I'm trying to get to 4.
Start with,
That's it.
that's it.
Okay.
Easy. The better your synthesis is, the more likely you are to get points. If you develop a synthesis that then gives you like 1% yield, probably won't be.
Do you want like air pushing as well as a synthesis?
No, in fact, if you just actually just put steps, I would be okay with that. Or yeah, I would recommend that you probably draw the structures just for yourself. So that okay, it's an individual, therefore. Right, ready? Ready? One more minute. Remember, take into consideration that this very acidic. So you don't want that messy. Alright, good? Now. Got it?
Hope so.
Alright, so now what I want to do, before I forget, let me give you guys the homework.
Wait, for this problems, are we supposed to be able to split the nucleotide, or were we just supposed to add the methyl?
Just add it right at the CH right here.
Oh.
Yeah, it's
Yeah,
really rotating.
never mind. So,
What do you mean, rotate?
never
It's
mind.
just,
Yeah, I was thinking about
It
saying
was
it
writing backwards,
Yeah.
Oh, here?
Yeah.
Yeah.
Oh, sorry, I thought you.
Yeah.
Okay, got it.
Yeah, remember this is what, anti or syn conformation?
Yes.
Syn, remember the anti is always where the Watson Crick base pair is exposed to it. Okay, so homework for next time is, let's see, the reference in the folder. Okay, so mechanisms for all of these things. Basically, 2 to 8. So basically 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, 7 to 8. I think everything is pretty straightforward. We definitely cover it. If we have it, you can definitely do it. Questions? So that's, these are the. Yeah, it will be that one.
These are due next Tuesday.
Next Tuesday, yeah. Okay. So now. Alright, so now what I want you guys to go over is scheme 2, scheme 3 on the worksheet you guys right now. And let's start with those two schemes right now. And then let's start by looking at the reagents and make sure that you can do all of these transformations. Let's start by looking what is it that it's doing. So for instance, 4 to 5, what do you do? Protects what position?
5 prime alcohol.
5 prime position with 3 group, right? Then B,
Protect the 3 prime, yeah.
there's the 3 prime in the presence of imidazole. Imidazole is a base, right? Then C and D.
So
That's a radical,
Yeah, I think you
that's,
brominate with a radical mechanism in C, and then you do a substitution of some sort of. You substitution.
You do as yeah. Yes, it does, yeah. So MBA is AIPN, remember that's radical, then you put a bromine there. what structure of MB is? You guys know? The bromosuccinamide, the MEA, you guys know. Okay. EF, what's EF?
TBS protection.
If you look at the transformation, what's 7 to 8? What is it doing?
Replacing the ketones with the NH2.
Right, so basically you go from uridine to cyclidine, right?
Mm.
That's a very common strategy. I think in the past, in the previous one, you guys can look that up, but in the previous one, we had something that one of the papers that I wrote, what is it? So I can remember what I gave you guys.
I have a Chem Bio and or papers.
It was
Which
the
one has to give you another-
Orglet one.
What is it?
You're talking about the mechanism you did last week?
Yeah,
You showed us how to lock the position of the ride.
right, so it was also from uridine to cyclidine, right?
Yeah.
But in that particular case was with focal 3.
Yeah, PCl3 and hydroxide and methanol.
Mm-hmm. You have something like this, and this is another strategy. For what you can see is one of the, in this particular case, it's acetylated. This is the organic layer step. It's acetylated. Where is it? There's no oxygen here. This was the point, right? But the main thing was that you treat this with focal 3, we want to have triazole. Then you follow this with ammonia, dioxane, and then ammonia, and then one common small dioxin. So what you end up getting is that's the main thing. Now, so you can see this is the exact same thing again, converting uridine to cyclidine. So it's a deamination. I mean, which position is this? You know that? So then focal 3, basically this is going to be added. Focal 3 was the structure of focal 3.
Just the sixth position.
As you can imagine how in the first step, it's kind of go there, and eventually you kick it up, and now you have a good leading group. You have your triazole. And the triazole is essentially going to attack here. So you're going to put a triazole here in this particular case. You put your triazole in this particular case, and then you have ammonia. Ammonia basically does nucleophilic aromatic substitution. Remember, these are all aromatic, so that's the idea. So you position a good leading group, and you have your nucleophilic aromatic substitution. Right, so now in this particular case, there are different conditions, so certainly see what these conditions are all about. Okay, so you transform uridine to cytidine, then what happens next? Basically G, 8 to 9.
Acetylation.
Yeah, you use acetylating the isocyclic then H,
Protect the TPSO, so
using
the TBAC,
EBAC, which is
acidic.
Fluorine.
chloride, removing ammonium chloride, then you phosphorilation, right, to get your phosphoramide. Any questions?
Wait, I'm still kind of confused. What happens after the triazole is replaced to carbonate?
So in the next step, we have essentially ammonium hydroxide, essentially ammonia in water. So you just have your NH3, Mesenheimer complex, is compact and kicks out the triazole, which is a really good. So that's how you position your exocyclic amine. Alright, so yeah, I think this was pretty straightforward. So let's go to the next one. So scheme 3, what is scheme 3 does? What's A?
Acetylation.
A is acetylation, and what do they do first? Basically 11 to 12. It's 2 steps essentially, right?
Mm-hmm.
What's the first step?
Protect the 5' and the
Protecting 5' and 3'. And then the second step?
protect the 2'.
Okay, 2' with CVS chloride. Then you look at B and C. What do you have B and C?
Acetylation.
There was before, right?
Yeah.
Then D and E. What's D?
Deacetylation.
What is D for?
Protecting the acetylation, just making an alcohol.
In the presence of base. Right? So really mild base. You can see here potassium carbonate, which is a very mild base, does the trick. And then E.
Alcohol to an aldehyde.
Mm-hmm.
It doesn't matter.
Yeah, it's multi-primate. So also one of the other things that you should look into is like the transformations, the synthetic steps, which you know mostly everything. So most of the things that we will see, you have seen. I mean, except for this is like the transformation of uridine to cytidine, but it's nothing at all. So nucleic acid chemistry is basically very ordinary chemistry, but it's challenging in the sense that you have to consider a lot of protective strategies, right? So that's one thing I want to point out. So okay, yeah, the DMP is multiprimate. What's F, 15 to 16?
Tetrahedral.
Yeah, what do they use?
Propyldiol.
1,3-propyldiol and
Trifluorophormate. 1,4-formate. Yeah, for formation.
so what type of chemistry is this?
Use this.
The chloride and Lewis acid. Can you do that mechanism?
Mm-hmm.
Also. And then G, followed by H, is what?
Carbonate to
Yeah, same thing as, well, different, right? So certainly look up what TPS is, what is that strategy. And so, yes. So that's basically the step. So you go to the next page. So 11 to 21, what's A? Relation, so you know what 11 is, right? So then what's 21 to 22?
Protection of both the 2'
Protection of
and
both
3'.
alcohols. PBS. CD is one, exact same thing. EF, exact same thing.
Yep.
Right? G, which is 24 to 25.
Subdivision.
Yeah. It's basically all the exact same thing, right? So, are there any questions on that? All right, so then let's go to the next one, scheme 5. So that's so in this particular case, the log that nucleic acid. So oftentimes under certain conditions, you can position a very good living group. There's more than one strategy. If you position a very good, let's say a liquid prefect here, if this is protected, then this can actually attack you. And then it leaves. Right, that's what you're seeing here in your first step. Okay. This is the first step. This oxygen, C2 oxygen, is attacking this position. Right? That's one strategy that's commonly done. There are other strategies, but in this case, they start with 11. So that would be the one precursor. So 11 to 12, what do they do? In the presence of
Is that a protecting strategy that you described? It's just like leaving all attacking to like protect that carbon swap potential.
well, in this particular case is to do chemistry on this. So what you see, for instance, what's 13
Yes, the alcohol.
is the arabinol. So it has been there has been an inversion. It's an epimer, and so that this is basically setting it off. All right. So we have ventilation in the presence of sodium hydride, right? So pretty straightforward. What's B? B protection.
It's DP, so oxidizing.
It's clean when you get the arabinol. So how do you do that mechanism?
Yeah.
B. So 12 to 13, 12 to 13. 12 to 13. So this base,
Yeah. Attach the
So
site.
it's basically potassium hydroxide, right? So what do you get? Can you get the arabinol? So the arabinol, the ribo is where you have the OHs here. The arabinol is the epimer where you have these all, right? And then the nucleobase or nothing. This is just no matter what you have here. This is ribose. This chemistry is the arabinol. Because now you have the epimer of this. Remember, epimers are called the one. Is the arabinol. In this case, they get the arabinol compound. So how do they get it? Can you do that mechanism? Yes? You can propose something? Okay, so I'm going to leave it up to you then. So then what C?
DMP.
Oxidation, yeah, and then D? Yeah, make an epoxide, but not only an epoxide, you have what else is going on there?
Adding an extra carbon in.
Yeah, an extra carbon. So how does that occur?
Probably the DMSO. Or I guess.
The DMSO.
Yeah, the trimethyl.
Yeah.
The trimethyl SOI.
Will it just like deprotonate one of the H's there? With that
It's going to the protonate, one of the H's, yeah.
Okay.
Where, so can you guys propose a mechanism for that?
Try.
this. I think the rest is really straightforward. Yeah, so the very let's work on those two mechanisms. So propose a mechanism for 12 to 13, and then a mechanism for 3 to 14, where the primitive SOI like this. Is the primitive SOI. And the key there, yeah, there's going to be a deprotonation. You have sodium hydride. Sodium hydride is deprotonating what? How do you get the epoxide? Alright, so let's work on this. I guess one clue there is that the leading group is going to be dimethyl sulfoxide. So DMSO. DMSO is a solvent, but in this particular case, DMSO, it's up as a leading group. And that's one of the driving forces. That's a good thing.
Can I ask, why did it add DMSO to it then, if like, it's leaving as dimethyl sulfoxide? So it's not the same thing?
Well, it's probably solubility.
Okay, so it's really like a dry solvent then? Okay.
Polar electron.
Yeah.
Oh, shit.
That's what's in the original. I like that.
All right, so you guys are good on that? Kind of. Protonate, this is nucleophilic, attacks your carbonyl. And then at that point, you can eliminate the MSR. Protonate, attack carbonyl, and then you can eliminate the MSR. That's the key. How to get that step. Okay, let's go into this step. This comes from, then I don't have it. Well, I'll give you the DOI. Sometimes look at this. DOI or one, the O, it's a Jerry OC technology. One, 9, 4, 4. So this is the DOI for this reference production. You can find it a bit more helpful. So certainly check on the synthesis again how they're incorporating a fluorescent probe on this DNA. But what I want to cover here is this step. So what is going on here? What is the product?
Nitro, then nitro group.
You put a nitro group where? On the ring? Where?
The meta position.
Meta to what?
Meta to the carbonyl. I don't know.
So what's the mechanism? Is what? Yeah, nitro is, so it's a nitration via
This is EAS.
an electrophilic aromatic substitution. Kind of. Okay, so now the question is the following. You can certainly look at the answer, right? But these are your two options on the nitration. Right, so typically if you treat a ring, remember benzene, or you see in organic chemistry, you have CONO2, which is essentially nitric acid and sulfuric acid, you nitrate the ring. Via an electrophilic aromatic substitution. Now this is essentially an electrophilic aromatic substitution. You can functionalize the 5 position or the 6 position, so which one do you get? You look at the paper, you'll see that you get which one would you predict?
I'm gonna go with 2.
And I will say the following. By looking at it, I think it'll be pretty tough to actually. Unless you have a really good vision of resonance structures.
So it's
How would you solve the problem?
resonance structures.
The resonance structures based on what? Like carbocations, right? So what you're going to see if you look at the paper is that they get in good yields and then they can do the amine. What you get, in this case, this is the major. That's another question is can you justify it? Yes? You guys sure? Alright, so I really don't have enough time for it. Yeah, so how would you go about doing this? Like electrophilic harmonic substitution, let's just treat it with an electrophile. So, two options, if we do how we do. So if this attacks an electrophile, it's gonna do this as an E, as electrophile. In this case, with CONO2 is actually an electronic ion, right? So it's the NO2 plus, the G as your electron. This is going to attack there. That's your nitration. That's your electrophilic reaction. So already we have seen with these types of rings are aromatic. So we already see nucleophilic aromatic substitution. Now we're seeing electrophilic aromatic substitution. So you take advantage of these aspects to functionalize the nuclear rings. Well, we've seen a little bit how to functionalize our strategies of how to do chemistry at the rivals. You can also do chemistry at the nuclear rings. So if you do that type of reaction, you have two options. One, where your electrophile is obvious. With NO2, that's your electrophilic species. With a carbocation there, versus there. Right, so those are your two options. So then which one do you get? I mean, I already told you the answer, but can you justify that? Right, so as a consequence, is it the same with uridine? Do you expect the same to occur with uridine? Right, so if you were to nitrate or uracil, would you predict the same thing? If you do adenosine or adenine, right? So where do you oxidize? Or where do you do chemistry? So in the case of uracil, two options, right? C5 and C6. In case of adenine, two options. What are your options? There and there. What are the numbers?
7, 8.
You start here, right? 1, 2, 3, 4, 5, 6. So C2 and it needs to be automatic. That's a good guess. Close. But no. 1, 2, 3, 4, 5, 6, 7, 8. So C2 or C8. So where do you do chemistry via electrophilic aromatic substitution? C2 or C8? Why? What about 1 or C? One
C8.
C8, right? Another option. So then the question is, can you justify that you get this nitration? You get the same outcome if you do it with uracil. What about uridine or adenine? You will C2 or C8, right? So how do you do that? You will draw your electrophiles. This is basically typical electrophilic harmonic substitution that you do with benzene. Then you have to do resonance structures and see if you can justify that. Are there any questions? No?
So the homework is just to create.
The homework is just this one. The rest is for your own personal. Yeah. Are there any questions on this? No?
What day is the homework due and what day is the quiz?
The homework is due on Tuesday.
Okay.
The quiz is probably going to be on Thursday.
Okay.
Next week. And I'm really hoping that the quiz will be on mainly synthetic aspects. I'm really hoping to jump onto some applications, of course, relying on the text. Right? So towards next week, I'm hoping to prepare a package of papers